Did you know that some of the most famous facts about space you've heard are completely wrong? From Hollywood movies to bedtime stories, we've all grown up believing certain myths about the cosmos, ideas so deeply ingrained that even astronauts might hesitate before questioning them. But what if I told you that many of these so-called truths have been utterly debunked by scientists? The universe is stranger, wilder, and far more fascinating than the tales we've been sold. And today, we're pulling back the curtain on 30 of the biggest space myths that just won't die, myths that even the smartest among us still fall for. Think about it. How many times have you heard that the Great Wall of China is the only human-made structure visible from space, or that the sun is a giant ball of fire? These ideas sound convincing, even poetic, but they're flat-out false. Science has proven them wrong, and yet they persist, passed down like cosmic folklore. Why? Because space is mysterious, and myths fill the gaps in our understanding with drama and simplicity. But the real story, the one written by cutting-edge research and hard evidence, is infinitely more thrilling. So buckle up. Over the next few minutes, we're taking a journey through the most stubborn space myths and the surprising truths behind them. You'll walk away with a whole new perspective on everything from black holes to the color of the sun, no advanced degree required. This isn't just about correcting misconceptions, it's about rediscovering the universe with fresh eyes. Because when we let go of what we think we know, we make room for something even better: wonder. Ready to have your mind blown? Let's dive in. Here's one of the most persistent myths about our closest cosmic neighbor: the idea that the so-called dark side of the moon is forever shrouded in darkness. It's a phrase that's been repeated in songs, movies, and even casual conversation, painting this mysterious half of the moon as a place where sunlight never touches. But here's the reality: that entire notion is completely wrong. The truth is, the moon is tidally locked to Earth, meaning one side always faces us while the other remains hidden from view. But that far side isn't trapped in eternal night. Just like the side we see, it experiences day and night cycles as the moon orbits Earth. Think about it. When the side facing us is in full shadow during a new moon, the far side is actually bathed in sunlight. And when we see a full moon, the far side is the one plunged into darkness. NASA lunar orbiters have captured stunning images of the so-called dark side illuminated by the sun, proving it's anything but permanently dark. So why do we still call it the dark side? Blame it on history and pop culture. The term stuck because we couldn't see that half of the moon until spacecraft like the Soviet Luna 3 probe gave us our first glimpses in 1959. Until then, it was literally the unknown side, and the name just lingered. But now we know better thanks to missions like the Lunar Reconnaissance Orbiter, which has mapped the entire lunar surface in incredible detail. Next time someone mentions the dark side of the moon, you can set the record straight. It's not a realm of endless night, it's just the side we don't see, cycling through sunlight and shadow just like the rest of our cosmic companion. And honestly, that makes it even more fascinating, because what's out of sight doesn't have to be out of light. Now let's tackle another myth that just won't go away: the idea that the Great Wall of China is the only human-made structure visible from space. It's a claim repeated in textbooks, documentaries, and even by well-meaning teachers trying to impress upon us the scale of this ancient marvel. But here's the twist: astronauts, satellite images, and basic physics all agree it's simply not true. Why does this myth persist? Part of it comes down to misunderstanding what visible really means from orbit. The Great Wall is long, stretching over 13,000 miles, but it's also narrow, averaging just 20 to 30 feet wide. From low Earth orbit, where the International Space Station circles about 250 miles up, the human eye struggles to pick out something that thin against the sprawling landscape. It's like trying to spot a single thread of spaghetti from the top of a skyscraper. Even astronaut Chris Hadfield, who spent months aboard the ISS, confirmed that without magnification, the wall blends into the natural terrain. Satellite imagery tells the same story. While advanced cameras can detect the wall under perfect lighting conditions, it's far from standing out. Cities, highways, and even large agricultural fields are far more noticeable from space. The myth likely started centuries before spaceflight, when people imagined the wall's grandeur must match its reputation, but reality is humbler and more fascinating. The wall's construction materials, often local earth and stone, make it blend seamlessly with the surrounding mountains and deserts when viewed from above. But here's what is visible from space: human impact on a massive scale. Vast urban sprawls, deforestation patterns, and even the glittering nighttime lights of major cities are unmistakable. The Great Wall's invisibility isn't a slight against its engineering, it's a reminder that from space, our planet tells a bigger story than any single structure. So next time someone claims the wall is visible from orbit, you can share the real cosmic perspective. Earth's beauty lies in its intricate tapestry, not just one thread. Hollywood has conditioned us to believe that stepping into space without a suit means instant, dramatic explosion, a gruesome fate shown in countless sci-fi films. But the real science behind exposure to the vacuum of space is far stranger and, honestly, less cinematic. While it's absolutely deadly, the human body doesn't pop like an overinflated balloon. Instead, the effects are a chilling mix of biology meeting physics, playing out in ways that defy movie logic. First, let's talk about what actually happens. In the vacuum of space, there's no atmospheric pressure to keep your body's fluids in check. Your skin is tough enough to prevent explosive rupture, but fluids in soft tissues like your eyes, tongue, and lungs start to vaporize. Swelling occurs, but not enough to tear you apart. Your body would bloat, your blood might bubble, and you'd likely lose consciousness within 15 seconds due to oxygen deprivation. But here's the twist: if you are rescued within about 90 seconds and repressurized, survival is possible. NASA's own research, including a tragic accident during a 1965 vacuum chamber test, confirmed this timeline. A technician survived nearly a full minute of near-vacuum conditions after his suit failed, later describing the sensation as feeling saliva boiling on his tongue before blacking out. The real danger isn't instant disintegration, it's the silent, suffocating lack of oxygen and the brutal cold of space. Without a suit, your lungs would collapse as gases expand, and your skin would face extreme temperature swings, from scalding in sunlight to freezing in shadow. But none of this resembles the Hollywood spectacle of bodies bursting like fireworks. Even the infamous scene in 2001, A Space Odyssey, often praised for its realism, exaggerates the effects for drama. So why does the explosion myth persist? Because it's visceral and simple, a quick, shocking end that fits the pacing of movies. Reality is slower, messier, and in some ways more horrifying in its quiet inevitability. But understanding the truth matters. It reminds us that space isn't just a backdrop for action scenes. It's an environment with rules that demand respect. And those rules, while less flashy, reveal just how resilient and fragile the human body really is. One of the most stubborn space myths of all time claims humanity never set foot on the moon, that the Apollo landings were an elaborate hoax filmed on a soundstage. It's a conspiracy theory that refuses to fade, despite overwhelming evidence proving otherwise. But here's what's fascinating. Science has quietly dismantled every single argument moon landing deniers use, often with tools you could replicate yourself. Take the myth that no stars appear in the lunar photos, proving they were staged. In reality, the Apollo cameras were set for daylight exposure, just like your smartphone struggling to capture dim stars next to a bright streetlight. The lunar surface reflects so much sunlight that exposing for stars would have washed out the entire scene. Astronomers confirm this basic photography principle daily. Then there's the waving flag claim. Conspiracists insist the flutter proves a studio fan was blowing it. But watch closely, the flag moves only when astronauts touch it, then settles instantly. Without air resistance, momentum alone causes that brief motion, something physicists demonstrated with vacuum chamber tests. The real clinchers, though, are experiments still running today. Apollo crews left laser reflectors on the moon, devices any major observatory can bounce beams off to measure Earth-Moon distance down to the millimeter. If these weren't there, scientists wouldn't get consistent returns for over 50 years. Plus, lunar samples brought back have compositions impossible to fake. They contain isotopes created only by prolonged cosmic ray exposure, lack Earth's water and rust, and match meteorites blasted off the moon naturally. Even the Soviet Union, America's Cold War rival, analyzed Apollo rocks and confirmed their authenticity. Perhaps the most damning evidence, thousands of NASA employees and contractors would have needed to stay silent for decades, a scale of conspiracy that defies logic. Meanwhile, lunar reconnaissance orbiters have photographed Apollo landing sites, showing descent stages and astronaut footpaths exactly where mission logs placed them. The truth isn't just in official records, it's etched into the moon's dust, visible to anyone with a telescope powerful enough to see lunar details. So why does this myth persist? Partly because space travel feels unreal. It's easier to distrust than to grasp the ingenuity behind it. But each piece of evidence, from laser beams to moon rocks, tells the same story. Human hands once touched another world and left proof even the most stubborn skeptics could verify if they chose to look. The real conspiracy isn't about faking achievement, it's about underestimating what humanity can do when we aim beyond Earth. Look up at the sky on a clear day, and you'll swear the sun is yellow, maybe even orange at sunrise or sunset. It's how we've drawn it since childhood, with crayon yellow circles and radiating lines. But here's the cosmic plot twist: the sun isn't yellow at all. In reality, it's a blinding white star, and the only reason it appears colored to our eyes is because Earth's atmosphere plays tricks on us. The truth lies in the physics of light. When sunlight enters our atmosphere, it collides with gas molecules and scatters in all directions, a phenomenon called Rayleigh scattering. Shorter wavelengths, like blue and violet light, scatter more easily, which is why our sky looks blue during the day. But here's the catch: this scattering also steals some of the sun's blue light, leaving the remaining direct light skewed toward warmer tones. Think of it like a cosmic filter. By the time sunlight reaches your eyes, it's lost enough blue to appear yellowish, especially when the sun is low on the horizon. But step outside Earth's atmosphere and the illusion vanishes. Astronauts and satellites see the sun for what it truly is, a blazing white orb. Spectrometer readings from space confirm this. The sun emits light most intensely in the green-yellow part of the spectrum, but when all its wavelengths blend together, our eyes perceive it as white. Even NASA, a solar dynamics observatory which captures high-resolution images of the sun, shows it in crisp white detail. So why does the myth persist? Blame it on human perception and artistic tradition. Our brains adjust colors based on context, and surrounded by a blue sky, the sun seems warmer in tone. Plus, staring directly at the sun is dangerous, so we only glimpse it fleetingly, often through layers of haze or pollution that further tint its light. But the next time someone hands you a yellow crayon to draw the sun, you'll know better. The real color is far more brilliant, a pure, unfiltered white, shining with the raw intensity of a star that defies our earthly illusions. And here's something even more mind-bending. That white light contains every color of the rainbow. When sunlight passes through a prism or raindrops creating a rainbow, it splits into its full spectrum. The sun doesn't pick favorites, it gives us all the colors at once. So while our atmosphere might paint the sky with blue and the sun with gold, the universe keeps its own palette, one that's far more dazzling than we ever imagined. Black holes have been branded as the ultimate cosmic monsters, unstoppable forces that suck in everything around them like interstellar vacuum cleaners. But this terrifying image is more myth than reality. While black holes do possess immense gravitational pull, their influence behaves far differently than science fiction would have us believe. The truth is, these mysterious objects follow the same universal laws of gravity as planets and stars, just taken to extremes. Let's break it down. Every massive object in space exerts gravitational force, whether it's a planet, a star, or a black hole. What makes black holes unique isn't some supernatural sucking power, it's their density. Imagine crushing the entire mass of our Sun into a sphere just 6 kilometers across. That level of compression creates a gravitational field so intense that within a certain boundary, known as the event horizon, not even light can escape. But here's the key: outside that boundary, a black hole's gravity behaves just like any other object of its mass. If our Sun suddenly became a black hole, keeping its mass but shrinking to a tiny speck, Earth would continue orbiting it normally, unharmed. The same gravity that holds us in orbit now would still be at work. This misconception likely comes from how we visualize black holes as swirling voids dragging everything toward them. In reality, matter doesn't get sucked in passively. It has to come close enough to cross the event horizon. Even the supermassive black hole at the center of our galaxy, Sagittarius, a star, doesn't indiscriminately devour stars. Astronomers have tracked stars like S2 orbiting it for decades, tracing graceful elliptical paths completely unaffected by the black hole's pull unless they stray too near. Simulations from NASA and the European Space Agency show these orbits mirroring Kepler's laws perfectly, proof that black holes don't rewrite physics. So why do we picture them as cosmic vacuum cleaners? Partly because their edge, the event horizon, is a point of no return. But crossing it requires getting dangerously close, just like a ship avoiding a whirlpool must skirt its edges. In deep space, where distances are vast, the chances of random objects falling in are slim. Even when matter does spiral toward a black hole, it often forms a glowing accretion disk first, feeding in gradually rather than vanishing instantly. The real wonder isn't their destructive power but their precision. Black holes are less like voracious monsters and more like cosmic scales balancing gravity's rules on an unimaginable scale. Next time you hear one described as a vacuum cleaner, remember, the universe is tidier than that. These enigmatic objects don't defy the laws of physics. They magnify them, showing us just how finely tuned the cosmos really is. It seems logical to assume the closest planet to the Sun would be the hottest after all. Mercury orbits a mere 36 million miles from that blazing furnace. But space loves defying expectations, and here's the twist: tiny Mercury isn't the solar system's heat champion. That title goes to Venus, a planet twice as far from the Sun, wrapped in clouds that turn it into a pressure cooker hotter than a pizza oven set to maximum. The difference comes down to atmospheres, or the lack of them. Mercury's a bare rock with virtually no air to trap heat. Sunlight strikes its surface unimpeded, baking temperatures up to 430 degrees Celsius during the day. But without an atmosphere to act like a cosmic blanket, that heat vanishes instantly when the sun sets. Nighttime temperatures plummet to minus 180 degrees, swings more extreme than any desert on Earth. NASA Messenger probe, which orbited Mercury from 2011 to 2015, recorded these wild fluctuations, proving how quickly heat escapes into space when there's nothing to hold it. Now consider Venus. Its thick, choking atmosphere, mostly carbon dioxide with clouds of sulfuric acid, works like an oven door locked shut. Sunlight penetrates those clouds and heats the surface, but when the ground tries to radiate that energy back into space, the greenhouse gases trap it. The result, a constant global temperature of 465 degrees, hotter than Mercury's peak, and steady day and night. Soviet Venera probes that landed there in the 1970s barely survived 2 hours before melting, their instruments relaying back data of a world where lead would pool into puddles. Here's what's wild. Venus's atmospheric pressure is 90 times Earth's equivalent to being nearly a kilometer underwater. That dense air acts like a heat-distributing fluid, smothering the planet in uniform scorching temperatures. Even Venus's poles are as hot as its equator, and its mountaintops, yes, it has mountains, roast just as fiercely as its valleys. Meanwhile, Mercury's airless peaks and craters alternate between inferno and deep freeze within hours. So why does this myth endure? Probably because proximity feels like it should equal heat. But the cosmos doesn't play by our intuitions. Venus teaches us that sometimes what covers a planet matters more than how close it sits to the fire. It's a reminder that in space, the rules get rewritten often in ways that leave our assumptions smoldering in the ash. Next time you picture the solar system's furnace, don't look to the sun's doorstep. Glance instead at that deceptively bright evening star, where an atmosphere turned paradise into purgatory. Mercury may be quick-footed around the sun, but Venus is the one truly burning up the cosmic dance floor. We've all heard the classic line, "In space, no one can hear you scream." It's been hammered into pop culture as an absolute truth. Space is a silent, soundless void. But what if that's only half the story? While it's true that the near-perfect vacuum between stars and planets can't carry sound waves like Earth's air does, the universe has a sneaky workaround. Under the right conditions, sound doesn't just exist in space, it thrives, resonating through cosmic environments in ways that would shock anyone raised on Hollywood's silent space battles. Take Saturn, for example. NASA Cassini spacecraft didn't just photograph the gas giant's majestic rings, it listened to them. Using instruments designed to detect plasma waves, scientists converted electromagnetic vibrations into audible sound, revealing something extraordinary. Saturn's rings produce eerie, ghostly whistles and hums as particles collide, creating pressure waves that travel through the planet's magnetosphere. These aren't sound waves in the traditional sense, they're vibrations in charged gas or plasma, which can carry energy just like air molecules do. When translated into frequencies our ears can process, the result is a haunting chorus that defies every silent space trope. But Saturn isn't alone. The sun's corona buzzes with ultra-low frequency roars, and black holes emit pressure waves that, when scaled up, produce notes 57 octaves below middle C, the deepest sound in the universe. Even the sparse gas between galaxies can transmit sound, albeit at frequencies millions of times lower than humans hear. The key difference: Earth's sound needs air, but space's sound rides on plasma, magnetic fields, or dust clouds. It's less like a shout and more like a ripple in an invisible ocean of charged particles. So why does the myth of silent space persist? Because most of the cosmos is quiet to human ears. But silence isn't emptiness, it's a lack of the right medium. Just as fish can't hear shouts from the shore, we're deaf to most cosmic vibrations without technology to translate them. Yet thanks to probes like Cassini and Juno, we've peeled back the curtain on a universe humming with hidden symphonies. The next time someone claims space is soundless, remind them, it's not that there's no music, we just needed to learn how to listen. And here's the most poetic twist of all. If you stood on a plasma-rich world with the right atmosphere, you might actually hear the stars, not with the crackle of fire, but with the resonant hum of a universe that never stops singing, just in frequencies we're only beginning to understand. Here's something that might shatter your perception of astronauts floating effortlessly in space. That iconic image of weightlessness isn't caused by a lack of gravity at all. The reality is far more fascinating. What we call zero gravity is actually a constant state of free fall, with the International Space Station and its crew perpetually plummeting toward Earth, only missing it because they're moving sideways so fast. Think about it this way: gravity doesn't just vanish when you leave the ground. At the ISS's altitude of roughly 250 miles, Earth's gravitational pull is still about 90% as strong as it is on the surface. So why do astronauts appear weightless? Because the station is falling, and so are they. Imagine swinging a ball on a string in circles around your hand. The tension in the string keeps the ball from flying away, just as Earth's gravity bends the ISS's path into a curve. Now picture cutting the string. The ball would zoom off in a straight line. The ISS is like that ball, moving forward so quickly that as gravity pulls it down, the planet's curvature means the ground falls away beneath it at the same rate. The result, a never-ending fall where everything inside the station falls together, creating the illusion of weightlessness. You can see this principle in action during NASA Vomit Comet flights, where planes dive sharply to simulate microgravity for 20 to 30 seconds. Passengers float not because gravity disappears, but because the plane's descent matches the rate at which they'd naturally fall. The same physics apply to the ISS, just on a planetary scale. Cameras show pens, water droplets, and even astronauts drifting as if gravity has vanished, but it's the shared acceleration that creates the effect. This myth likely persists because zero gravity is a convenient shorthand, one even scientists use colloquially, but the truth reveals something profound. Orbit isn't an escape from gravity. It's a delicate dance with it, where speed and fall cancel each other out in perfect harmony. Next time you see footage of astronauts somersaulting through their module, remember, they're not beyond Earth's reach. They're in its embrace, hurtling forward fast enough to miss the ground forever. And here's the kicker: if the ISS suddenly stopped moving sideways, it would take less than an hour for gravity to drag it crashing back to the surface. That's how relentless Earth's pull really is. What looks like floating is actually falling with style, a reminder that in space, even the simplest truths are anything but ordinary. Think of every sci-fi movie scene where a spaceship swerves through a storm of asteroids, dodging massive rocks left and right. It's thrilling, it's dramatic, and it's completely fake. The truth about our solar system's asteroid belt is far less chaotic. Instead of a cluttered cosmic junkyard, it's more like a handful of pebbles scattered across an empty football field. The average distance between asteroids, roughly 600,000 miles, that's over 2.5 times the distance from Earth to the Moon. NASA missions through the belt, like Pioneers 10 and 11 or Voyagers 1 and 2, didn't need evasive maneuvers because the odds of hitting anything were astronomically low. In fact, when the Dawn spacecraft visited Ceres and Vesta, two of the belt's largest objects, it didn't encounter a single unexpected collision. That's because despite hundreds of thousands of asteroids, the belt's total mass is less than 4% of our moons, spread across an area so vast that most of it is just empty space. Even at its densest points, you'd struggle to spot a neighboring asteroid with the naked eye. The myth likely stems from early illustrations and films exaggerating the belt's density for visual drama. But real data paints a different picture. Japan's Hayabusa 2 mission, which rendezvoused with the asteroid Ryugu, had to carefully navigate for years just to reach its target, not because of obstacles, but because targets are so few and far between. The European Space Agency's Rosetta probe faced a similar challenge, spending a decade chasing Comet 67P across the belt without a single close call with another object. Here's a mind-bending comparison. If you stood on one asteroid in the belt, your chances of seeing another nearby would be like spotting a single car in the entirety of North America from the ground. That's how sparse it really is. The belt isn't a hazard zone, it's a testament to how much nothingness fills our solar system. So why does the crowded image persist? Because emptiness doesn't sell movie tickets or spark imaginations like a high-speed asteroid chase. But the reality is even more awe-inspiring, a realm where loneliness is the rule, and each drifting rock is an island in a sea of darkness. The next time you see a ship weaving through a fictional asteroid field, remember the real belt isn't a maze. It's a desert with dunes scattered so wide you could wander for lifetimes without crossing one. If you thought astronauts float in space because gravity vanishes the moment they leave Earth, think again. The reality is far more elegant and rooted in principles laid out by Isaac Newton over 3 centuries ago. That sensation of weightlessness isn't about escaping gravity's grip. It's about matching its pull so perfectly that you're in a never-ending dance with the planet below. Picture this, Newton's famous cannonball thought experiment. Imagine firing a cannon horizontally from a mountaintop. The harder you launch it, the farther it travels before hitting the ground. Now imagine launching it so fast that as it falls toward Earth, the planet's curvature means the ground curves away beneath it at the same rate. The cannonball never lands, it just keeps falling around the planet. That's precisely what's happening aboard the International Space Station. The ISS isn't beyond gravity's reach. It's falling continuously, with its forward motion ensuring it misses the Earth every time. Astronauts inside are falling at the same rate, so they experience the illusion of weightlessness. This ties back to Myth 9, where we debunked the idea of space as a zero-gravity void. Gravity doesn't switch off at some magical altitude. It weakens with distance but never disappears entirely. Even the Moon, nearly 240,000 miles away, feels Earth's tug, which keeps it in orbit. The difference is speed. The ISS hurtles around Earth at roughly 17,500 miles per hour, fast enough to balance the pull of gravity with its own momentum. It's not floating above Earth, it's falling around it in a carefully calculated trajectory. You can test this principle yourself with a simple experiment. Hold a marble at eye level and drop it, it falls straight down. Now toss it gently sideways. It arcs downward as gravity pulls it, but the horizontal motion makes the path curve. Throw it harder and the arc stretches farther. The ISS is just like that marble, thrown so fast that its arc matches Earth's curvature, creating a perpetual free fall where everything inside moves together. Here's the kicker: if the ISS slowed down, gravity would yank it back to Earth in minutes. That's how relentless the planet's pull really is. The magic isn't in defying gravity, it's in harnessing it, turning a cosmic force into the engine that keeps astronauts soaring. So next time you see footage of a crew member flipping effortlessly through their module, remember, they're not floating because gravity's gone. They're falling with such precision that they'll never hit the ground. And that's the real wonder of orbital mechanics. Full moons have been blamed for everything from erratic behavior to sleepless nights, with emergency rooms and police departments swearing they see spikes in chaos when the moon is bright. But here's the cosmic irony. Decades of rigorous studies have found zero consistent evidence that the moon actually influences human behavior. The so-called lunar effect is a textbook case of confirmation bias, our tendency to notice and remember events that fit our beliefs while ignoring those that don't. Take one of the most comprehensive analyses ever conducted, a 2019 review published in Current Biology, examining over 17,000 records across multiple continents. Researchers tracked sleep patterns, crime rates, and hospital admissions, comparing them to lunar cycles. The result: no meaningful correlation. Emergency rooms weren't busier, crimes didn't spike, and people didn't lose more sleep. Even folklore staples like werewolf myths or the term lunatic, derived from luna, the Latin word for moon, crumble under scrutiny. Historians point out these legends originated long before systematic record-keeping, when blaming the moon was as plausible as blaming bad weather for misfortune. So why does the myth persist? Part of it stems from selective memory. If 3 unusual events happen during a full moon, we link them, but the 100 other nights when nothing strange occurs, they're forgotten. Police officers recalling one chaotic full moon shift overlook dozens of quiet ones. Even scientists aren't immune. Early studies claiming to find lunar effects often cherry-picked small samples or ignored contradictory data. Later meta-analyses, like a 2016 study in nursing research, debunked these patterns by examining larger datasets. Turns out, when you account for random variation, the moon madness signal vanishes. Here's the clincher: if the moon's gravity can shift ocean tides, surely it could tug on something as fluid-filled as the human body. Right, wrong. The tidal force required to move oceans operates on a planetary scale. Your body experiences stronger gravitational pulls from passing trucks or overhead airplanes than from the moon. A study in the American Journal of Emergency Medicine calculated that a mosquito landing on your arm exerts more localized force than lunar gravity. The real story isn't about the moon's power. It's about humanity's love for patterns. We're wired to seek explanations, even in randomness. But science's job is to test those instincts, and here the verdict is clear. The moon lights up our nights, not our tempers. Next time someone warns you about full moon chaos, smile and remember the only thing the moon controls is the tide, and even that's a stretch when it comes to human drama. We often picture space as a perfect vacuum, an endless, empty void where nothing exists between stars and planets. But this couldn't be further from the truth. The cosmos is teeming with faint, invisible material, from wispy clouds of gas to microscopic dust, all floating in the vast expanses we mistakenly call empty. This interstellar medium might sound like cosmic clutter, but it's the very stuff that births stars, shapes galaxies, and even carries the faint afterglow of the universe's explosive beginning. Let's start with the gas. Nearly 99% of the interstellar medium consists of hydrogen and helium, remnants of the Big Bang so thinly spread that a cubic centimeter might hold just one atom. That's 1,000,000 times less dense than the best artificial vacuums on Earth, but it's not nothing. These atoms drift in enormous clouds, some spanning hundreds of light years. When gravity pulls them together, they collapse into glowing stellar nurseries. The Orion Nebula, visible to the naked eye, is one such region where this sparse gas has coalesced into newborn stars. Without these faint cosmic reservoirs, the universe would be dark and starless. Then there's the dust, tiny grains of carbon, silicon, and ice, each smaller than a wavelength of light. These particles might seem insignificant, but they're the universe's shadow artists. They scatter and absorb starlight, creating the dark ribbons we see winding through the Milky Way. In some corners of space, like the iconic pillars of creation, dust acts as a cosmic curtain, hiding young stars while also protecting them from harsh radiation. Far from being empty, these dusty regions are bustling construction sites for planetary systems. But perhaps the most astonishing proof that space isn't empty lies in something we can't see at all: the cosmic microwave background radiation. This faint glow, discovered by accident in 1965, is the cooled remnant of the Big Bang's fireball. It fills every cubic inch of the universe, a whisper of light that's traveled for over 13 billion years. Modern satellites like Planck have mapped its subtle variations, revealing a universe that's textured with density fluctuations, echoes of the primordial soup that birthed galaxies. So why does the empty space myth endure? Because our eyes and telescopes evolved to see the bright spot stars, planets, galaxies, while the delicate fabric between them stays invisible without specialized instruments. But just as the air in a room goes unnoticed until the wind stirs, the interstellar medium shapes everything around it. It's the canvas on which the cosmos paints its grandest masterpieces, proving that what looks like nothing is often the most important something of all. Next time you gaze at the night sky, remember, the darkness isn't blank. It's alive with the faint breath of atoms, the silent dance of dust, and the ancient light of creation itself, all waiting to be discovered. Ask any stargazing beginner to point out the North Star, and chances are they'll scan the sky for the brightest pinpoint they can find. It's an easy mistake after all. Shouldn't the most important star in navigation also be the most dazzling? But here's the celestial reality. Polaris, the North Star, isn't even in the top 40 brightest stars visible from Earth. It's outshone by dozens of others, including Sirius, Vega, and even Betelgeuse. So why does this modest star, barely cracking magnitude 2, hold such legendary status? The answer lies not in its brilliance, but in something far more subtle: its steadfast position in a spinning sky. Polaris earns its fame through sheer cosmic geography. It sits almost perfectly aligned with Earth's rotational axis, making it the one star that never appears to move as the planet turns. While other stars wheel around the heavens through the night, Polaris holds its ground, a fixed point that's guided travelers for millennia. Ancient Phoenician sailors relied on it to navigate the Mediterranean, and Civil War-era freedom seekers used it to steer toward safety along the Underground Railroad. Its utility has nothing to do with brightness, it's about reliability. Picture it like a lighthouse whose power isn't in the intensity of its beam, but in the certainty of its location. Compare that to Sirius, the actual brightest star in Earth's night sky. At magnitude -1.46, it blazes with 25 times the luminosity of Polaris. But Sirius dances across constellations, rising and setting like any other star. Vega, another luminary outshining Polaris by nearly 6 times, follows a similar path. Their brilliance might catch your eye, but they'd make terrible navigational tools. Their positions shift with time and latitude. Polaris, meanwhile, remains within 1 degree of true north, a consistent marker whether you're in Oslo or Oklahoma. This myth likely persists because we conflate importance with visibility. Modern light pollution exacerbates the confusion. Many city dwellers can only spot a handful of stars, so assuming Polaris must be among them feels logical. But venture to truly dark skies and the truth reveals itself. Orion's belt gleams brighter, Arcturus burns like an amber ember, and there, nestled between the Big Dipper and Cassiopeia, Polaris humbly holds its post, a steady sentinel in a glittering, shifting cosmos. There's poetry in this cosmic underdog story. Polaris doesn't need to outshine its stellar neighbors to matter. Like a silent guide in the wilderness, its power isn't in shouting for attention, but in being there when everything else is in motion. Next time you navigate by the stars, remember, sometimes the most critical markers aren't the flashiest, just the ones you can count on, night after night, century after century. One of the strangest myths about space suggests astronauts can't see stars from orbit, a claim usually supported by pointing to pitch-black Apollo mission photos where no stars appear. But the truth hiding in those images isn't about visibility. It's about cameras struggling to balance exposures when faced with overwhelming brightness. The cosmos isn't shy about showing off its sparkle, it's our technology that can't keep up. Ask any astronaut who's gazed out a spacecraft window, and they'll describe a starscape so dense it feels like swimming through glitter. Chris Hadfield, during his time on the ISS, recounted how the unblinking stars outshone anything seen from Earth, undimmed by atmosphere or light pollution. Sunita Williams compared the view to a snowstorm of light, with constellations so vivid they erased all doubt about humanity's place in the galaxy. These first-hand accounts shatter the myth. Not only can stars be seen in space, they're more visible, their brilliance undiluted by the filtering effect of air. So why don't stars show up in so many NASA photos? Blame the challenges of cosmic photography. When capturing a bright lunar landscape or sunlit spacesuits, cameras must prioritize exposing for those highlights, rendering dimmer stars invisible in the process. It's the same reason you can't photograph stars from Earth with a smartphone pointed at a city skyline. The camera averages the light, drowning out faint points. But adjust the settings and the stars emerge. Hubble's ultra-long exposures, like the iconic Deep Field image, reveal over 3,000 galaxies in a patch of sky no bigger than a grain of sand held at arm's length. Even the Apollo crews took star photos when their cameras weren't overwhelmed by daylight. Lunar module pilot Alfred Worden described manually capturing star fields during the trans-Earth coast by carefully timing exposures. The irony, some of the clearest proof comes from footage the public rarely sees. ISS live feeds frequently show stars whizzing by during orbital night passes, and astronaut helmet visor reflections in moonwalk videos often glint with unmistakable pinpricks of starlight. Modern sensors on spacecraft like the James Webb Telescope have finally caught up to human eyesight, capturing the universe's glow without compromise. This myth persists because we confuse photographic limitations with reality. But the cosmos doesn't hide its jewels, it's our tools that need tuning. Next time someone claims space hides its stars, remind them the view from orbit isn't a barren void. It's the front row to the greatest light show in existence, where every glance out the window is a reminder of just how crowded and radiant the universe really is. Picture the Big Bang, and chances are you envision a colossal explosion. A fiery burst of matter erupting outward into empty space like a cosmic bomb. It's an easy image to latch onto, but here's the twist. Scientists didn't discover an explosion at all. What they found was something far stranger, a rapid, seamless expansion of space itself, stretching the universe from a hot, dense state into the vast cosmos we know today. The difference isn't just semantic, it rewrites how we understand the birth of everything. Think of it this way: a conventional explosion, like a firework or supernova, happens within space, hurling debris outward into a pre-existing void. But the Big Bang wasn't an event in space, it was the origin of space. There was no outside for it to explode into. Instead, space itself began stretching, carrying matter along with it like raisins in rising dough. This distinction explains why galaxies aren't flying away from a central point, but are drifting apart as the fabric between them expands, the evidence. Redshift, the stretching of light waves as distant galaxies recede, a telltale fingerprint of the universe's ongoing growth. Here's where the analogy gets even more mind-bending. If you could rewind the universe, you wouldn't find all matter crushed into a single fiery point like the center of an explosion. You'd find space itself shrinking, denser and hotter everywhere at once. The bang wasn't a localized detonation, it was the entire universe waking up, unfurling in every direction simultaneously. That's why we see cosmic microwave background radiation, the afterglow of that early heat, uniformly bathing the sky from all sides, not radiating outward from a single source. The explosion myth likely persists because it's visceral and familiar, but the reality is more like a magic trick where the stage, the audience, and even the magician are all part of the act. Next time someone describes the Big Bang as a cosmic fireball, remember, the universe didn't burst onto the scene. It became the scene, stretching into existence with a quiet elegance that makes explosions look clumsy by comparison. And that revelation, it's the real bang for your buck. For generations, textbooks and artists have depicted our Milky Way as a simple, elegant spiral galaxy arms gracefully curving around a central bulge like a cosmic pinwheel. But modern astronomy has torn up that old blueprint. Thanks to groundbreaking data from the European Space Agency's Gaia mission, we now know our galactic home is far more complex. A barred spiral with a warped, wobbly disk that defies the symmetrical beauty of classic illustrations. Gaia's precision mapping of over 1 billion stars has revealed the Milky Way's true skeleton. At its heart lies a dense, elongated bar of stars and gas stretching 27,000 light-years, a structure hidden from Earth's vantage point by thick interstellar dust. This central bar acts like a cosmic mixer, funneling gas toward the galactic center and triggering bursts of star formation. Surrounding it, our galaxy's spiral arms aren't the tidy, evenly spaced swirls we once imagined. They're messy, frayed tendrils of stars and dust, with our own solar system perched on the Orion Spur, a minor branch between the Perseus and Sagittarius arms. But the real shocker, the Milky Way's disk isn't flat. It's warped like a vinyl record left too long in the sun, with the outer regions bending upward on one side and downward on the other. Gaia's star catalogues show this twist vividly, likely caused by gravitational tugs from satellite galaxies like the Large Magellanic Cloud. Imagine a spinning pizza dough tossed into the air, its edges flaring unevenly as it rotates. That's our galaxy, a three-dimensional, misshapen marvel that rotates at 540,000 miles per hour while its edges ripple like cosmic waves. What's astonishing is how long this truth eluded us. Just as fish might struggle to map the ocean while swimming in it, Earth's position embedded in the galactic plane made seeing the big picture impossible until Gaia's billion-star census. By tracking stellar motions in 3 dimensions, astronomers reconstructed the Milky Way's structure like forensic sculptors, revealing dynamic processes no artist could have guessed. Young stars race along the bar's gravitational currents, while older stars bob above and below the disk in slow, wobbling orbits that betray the galaxy's turbulent past. This isn't just academic trivia. The Milky Way's true shape reshapes our understanding of galactic evolution. Bars drive gas toward supermassive black holes, fueling their growth. Warped disks hint at past collisions, ghostly imprints of smaller galaxies consumed long ago. Even our night sky looks different through this lens, those foggy bands of the Milky Way we see arching overhead. They're not neat spiral arms but tangled starlight filtered through the galaxy's twisted, uneven plane. Next time you see a smooth spiral galaxy in a documentary, remember, reality is gloriously untidy. Our Milky Way isn't a perfect cosmic clockwork. It's a living, twisting, dynamic beast, its form sculpted by billions of years of gravitational dances. And thanks to missions like Gaia, we're finally meeting our galactic neighborhood not as we imagined it, but as it truly is, flaws, twists, and all. Stargazers have long marveled at the twinkling dance of distant stars, a phenomenon so poetic it's inspired countless lullabies and love songs. But here's the cosmic truth: stars don't actually twinkle. That shimmering effect is entirely Earth's doing, a celestial magic trick performed by our own turbulent atmosphere. Step beyond it, and every star becomes a steady, unwavering beacon, their light finally free from the chaos of our air. The science behind this illusion lies in the way light travels through layers of atmosphere. As starlight passes from the vacuum of space into Earth's gaseous envelope, it encounters pockets of air with varying temperatures and densities. These act like invisible lenses, bending the light slightly with each ripple, a process called atmospheric refraction. Hot air rises, cold air sinks, and the constant mixing creates a flickering effect, much like looking up from the bottom of a swimming pool at a wobbly, distorted surface. The result, a star's pinpoint of light gets scattered, dancing unpredictably as it reaches your eyes. But the moment you leave Earth's atmosphere, the show stops. Astronauts aboard the International Space Station see stars as they truly are: crisp, stable points of light. Telescopes like Hubble, orbiting above atmospheric interference, capture razor-sharp images of stars without a hint of twinkle. This stability is why space-based observatories are so revolutionary. They remove the funhouse mirror effect of our air, revealing details invisible from the ground. A single star seen from space might unveil binary companions or subtle color variations that Earth's turbulence would have blurred into oblivion. The twinkling myth persists because, for most of human history, we've had no other way to observe the heavens. Even Galileo's telescope couldn't fully compensate for atmospheric distortion, but modern technology has peeled back the veil. Adaptive optics systems on ground-based telescopes now use lasers to measure atmospheric turbulence in real time, then deform their mirrors to counteract it, effectively untwinkling stars with computer precision. It's like giving the telescope a pair of glasses to correct its blurry vision. Here's the kicker: planets like Jupiter or Venus rarely twinkle, and that's a dead giveaway to their nature. Unlike distant stars, which appear as mere dots, planets occupy tiny disks in our sky. When atmospheric distortion bends their light, it affects different parts of the disk simultaneously, cancelling out the twinkle effect. Ancient astronomers used this clue to distinguish wandering planets from fixed stars, a trick still handy for backyard stargazers today. So next time you wish upon a twinkling star, remember, you're not seeing the star's true nature. You're witnessing Earth's restless atmosphere turning starlight into a performance. The real magic lies beyond our skies, where every star burns with a quiet, unwavering constancy. No flicker, no drama, just the pure, unfiltered light of the cosmos. And that reality, stripped of illusions, is far more breathtaking than any lullaby could capture. One of the most persistent space hoaxes claims that Mars will appear as big as the full moon in our night sky, a viral rumor that resurfaces every few years, often accompanied by breathless social media posts. But here's the cosmic reality. Even at its closest approach, Mars never grows larger than a pinprick of light to the naked eye. To understand why, let's break down the numbers in a way that puts this myth to rest once and for all. First, consider the actual distances involved. At its nearest, Mars orbits about 35 million miles from Earth. Compare that to our Moon's average distance of just 239,000 miles. That means Mars is roughly 150 times farther away than the Moon at minimum. Now picture this: hold a dime at arm's length. That's about the size of the full moon in your field of view. To appear equally large, Mars would need to be the same angular size, which would require it to either be 150 times bigger in diameter or somehow magically leap 150 times closer to Earth. Neither scenario is remotely possible. The math gets even more revealing when you examine angular diameter, how much space an object takes up in your visual field. The Moon spans about half a degree, 30 arcminutes in our sky. Mars, at its absolute closest, measures just 25 arcseconds. That's nearly 70 times smaller than the Moon's apparent size. Through a backyard telescope, you might glimpse Mars as a tiny rust-colored disk, but it would still look no bigger than a freckle on a fingertip held at arm's length. What makes this myth so stubborn? Partly it's wishful thinking. The idea that our neighboring planet could loom dramatically overhead is undeniably thrilling. The confusion may stem from a misinterpreted email from 2003, when Mars made an unusually close approach, the nearest in 60,000 years. Astronomers excitedly noted that through a modest 75-power telescope, Mars would appear as large as the Moon does to the naked eye. Somewhere along the way, that nuanced comparison got mangled into the false claim we still hear today. Here's a striking visual. If you lined up 100 full moons side by side, they'd stretch roughly the width of your outstretched hand. Now imagine trying to spot Mars in that lineup. It would be like finding a grain of sand on a dinner plate. NASA rovers may give us stunning close-ups of Martian landscapes, but from Earth, the red planet remains a modest dot, its modest glow no match for our Moon's radiant presence. So next time someone shares that viral Mars vs. Moon post, you'll know the truth lies not in the sky, but in the sobering vastness of space itself. The real wonder isn't in false comparisons, it's in appreciating each celestial body for what it truly is. The Moon, our constant companion, and Mars, a distant world whose faint light carries the whispers of a planet we're only beginning to know. We've all seen the classic images of Earth from space, a flawless blue marble hanging against the blackness, so perfectly spherical it could have been drawn with a compass. But here's the twist: our planet isn't the impeccable sphere we've been led to believe. Thanks to centuries of precise measurements, we now know Earth is an oblate spheroid, slightly squashed at the poles and bulging at the equator like a beach ball someone sat on. This subtle distortion isn't a defect, it's a dazzling consequence of physics in action, a cosmic fingerprint left by Earth's relentless spin. Picture a figure skater pulling their arms in to spin faster. As Earth rotates, that same principle applies on a planetary scale. The equator whips around at 1,000 miles per hour while the poles barely move. All that centrifugal force flings material outward, creating a bulge that makes Earth's diameter at the equator 26 miles wider than its pole-to-pole measurement. To put that into perspective, if Earth were shrunk to the size of a basketball, the difference would be less than 1/4 of an inch, imperceptible to the eye but monumental for scientists tracking satellites or calculating gravitational fields. Satellites like NASA's GRACE mission have mapped Earth's true shape with jaw-dropping precision, revealing a surface that's even more irregular than the oblate spheroid model suggests. Our planet is actually a geoid, a term describing a gravity-defined shape where the surface follows the pull of Earth's uneven mass distribution. Imagine a globe covered in subtle bumps and dips, where mountain ranges and ocean trenches distort the gravitational field like fingerprints on glass. The geoid isn't just academic trivia, it's the reason your GPS doesn't lead you into a lake. Satellites account for these gravitational wrinkles to pinpoint locations within millimeters. But here's where it gets even wilder. Earth's shape isn't fixed. Glacial melt, tectonic shifts, and even groundwater extraction subtly alter the planet's contours over time. When Greenland's ice sheet loses mass, the local sea level drops because the reduced gravitational pull lets water slosh elsewhere. Meanwhile, the rebound of land after Ice Age glaciers retreated continues to nudge continents upward like a slow-motion trampoline. These changes are minuscule year to year. Think the width of a human hair, but over millennia, they sculpt Earth's profile as surely as wind shapes a dune. So why does the perfect sphere myth endure? Because from space, the deviation is invisible to casual observation. Even astronauts orbiting at 250 miles up can't eyeball the bulge. It takes precise instruments to detect. But that slight imperfection is what keeps our planet stable, its balanced wobble allowing for seasons and climates that nurture life. A truly perfect sphere might look prettier in posters, but it's Earth's gentle flaws that make it uniquely habitable. Next time you see that iconic blue marble photo, remember, the real Earth isn't just a sphere. It's a dynamic, ever-changing masterpiece of physics, a cosmic lump that's perfectly imperfect. One of the most persistent myths about space travel claims the Van Allen radiation belts surrounding Earth are impassable death zones, lethal barriers that should have roasted Apollo astronauts alive. But here's what radiation data from those missions actually reveals. The danger was not only manageable but carefully planned for, proving human ingenuity can navigate even the harshest cosmic challenges. The Van Allen belts, discovered in 1958 by Explorer 1, are donut-shaped zones of charged particles trapped by Earth's magnetic field. They consist of two primary regions, an inner belt of high-energy protons and an outer belt of electrons, stretching from 600 to 37,000 miles above the planet. At their peak intensity, these belts can indeed deliver dangerous radiation doses, but only if you linger unprotected for extended periods. Apollo missions spent mere hours traversing them, slingshotting through the thinnest sections at high speed. NASA radiation badges recorded doses averaging just 1 to 2 rads during transit, less than a medical CT scan, and far below the threshold for acute radiation sickness. Modern spacecraft design has rendered the belts even less threatening. The International Space Station orbits safely beneath the inner belt, while lunar-bound missions like Artemis use precise trajectories to minimize exposure. Advanced shielding layers of polyethylene, aluminum, and even water-filled walls scatter and absorb particles before they reach crew cabins. Engineers now employ storm shelter protocols during solar flares, directing astronauts to shielded compartments until the particle storm passes. Even SpaceX's Dragon capsule incorporates radiation-resistant materials, proving private spaceflight takes the threat seriously. The myth likely stems from early uncertainties about the belt's intensity. Before direct measurements, some scientists feared they'd be impassable, but data from Pioneer 3 and Explorer 4 clarified their structure, allowing mission planners to chart safe paths. Apollo crews passed through the belt's least dense regions, their aluminum hulls blocking most particles. Later analysis showed their total radiation exposure was less than what airline crews accumulate over years of high-altitude flights. Here's the real kicker: radiation in deep space outside the belts poses a greater risk. Without Earth's magnetic field deflecting cosmic rays, astronauts face constant background radiation far beyond Van Allen levels. Mars-bound missions will need innovative shielding, possibly using magnetic fields or regolith-based habitats. Yet the Apollo era proved even mid-60s technology could conquer the belts with smart planning and precise timing. So next time someone claims the Van Allen belts are an impenetrable death trap, remember, they're just another cosmic obstacle humanity learned to navigate. The real story isn't about insurmountable danger, it's about how science turns unknowns into mile markers on the road to the stars. When you picture a comet streaking across the night sky, it's easy to imagine a fiery ball burning through space like a cosmic torch, but nothing could be further from reality. These celestial wanderers aren't flaming at all. They're more like dirty snowballs, colossal chunks of ice and rock left over from the solar system's birth, and their spectacular tails aren't made of fire. They're the result of sunlight turning frozen gases directly into vapor, a process called sublimation. The European Space Agency's Rosetta mission, which spent 2 years orbiting Comet 67P, gave us an unprecedented front row seat to this icy spectacle, shattering the fiery comet myth forever. Rosetta's close-up images revealed a surreal landscape of jagged cliffs and dusty plains, all made of water ice, carbon dioxide, and organic compounds. As the comet approached the sun, its surface temperature rose, and those ices began vaporizing without ever becoming liquid, like dry ice disappearing into fog. This vapor, mixed with dust, formed the comet's iconic twin tails, a bright, curved dust tail pushed by sunlight, and a faint, straight ion tail blown by the solar wind. Far from burning, the process is more like a cosmic freezer door left open, with frost evaporating into the void. The most startling revelation: Comet 67P's surface wasn't uniformly active. Rosetta captured jets of gas erupting from specific hotspots where sunlight hit exposed ice. These geysers, sometimes bursting with the force of small fireworks, sent plumes of material hundreds of kilometers into space material that later formed the comet's magnificent tail. Instruments on board even detected the scent of the comet, a bizarre cocktail of rotten eggs, horse urine, and bitter almonds, courtesy of sulfur, ammonia, and hydrogen cyanide in the vapor. Here's what's wild: comets aren't just passive lumps of ice. Rosetta's measurements showed their surfaces can be surprisingly dynamic, with landslides and shifting boulders reshaping the terrain as sunlight weakens structural bonds. The Philae lander, which famously bounced across the surface, discovered organic molecules essential for life, fueling theories that comets may have seeded Earth with water and probiotic materials billions of years ago. So why does the flaming comet myth endure? Blame the visuals. From Earth, a comet's glowing tail looks like a streak of fire, especially when sunlight scatters off its dust. But the truth is colder and far more fascinating. These icy time capsules, preserving the raw ingredients of the early solar system, don't burn. They whisper, their tails unfurling like cosmic breath in the solar wind. Next time you see a comet blazing across the sky, remember, you're not watching a fireball. You're witnessing the quiet, frozen heart of the solar system, finally warming up enough to say hello. Picture the universe not as an exploding firework with a clear center, but as rising raisin bread, one where every raisin moves away from every other raisin as the dough expands. This is the essence of metric expansion, the mind-bending reality that our cosmos doesn't radiate outward from any special point. The Big Bang wasn't an explosion in space, it was the expansion of space itself happening everywhere at once. That means no matter where you stand in the universe, every galaxy will appear to be racing away from you, with the most distant ones speeding off the fastest. Here's where the raisin bread analogy shines. Imagine unbaked dough dotted with raisins representing galaxies. As the bread bakes and swells, each raisin sees all others moving away. From any raisin's perspective, it seems to be the center, but the truth is there is no center, just dough stretching uniformly. This is precisely how our universe works. Hubble's observations in the 1920s first revealed this pattern. Galaxies recede from us in all directions, their light redshifted by the expanding space between us. But crucially, observers in any galaxy would see the same thing. The cosmic microwave background radiation seals the deal. This ancient glow, left over from the universe's early hot phase, bathes Earth with near-perfect uniformity, varying by less than 1 part in 100,000. If we were near some privileged center, the CMB would appear warmer in one direction and cooler in the other. Instead, it's equally frigid in all directions, like standing in a fog so evenly dense you can't tell where it thins. Maps from missions like Planck show this stunning symmetry, a smoking gun that the Big Bang's aftermath touched every corner of space identically. Dive deeper and it gets stranger. The universe's lack of a center implies it could be infinite, with no edge or special location. Even if finite, like the surface of a balloon inflating another useful analogy, it would still have no center within its dimensions. The balloon's surface is all there is, no inside or outside, just an expanding two-dimensional fabric. Our three-dimensional universe might behave similarly, with space itself stretching while eluding any middle point. This myth likely persists because our brains crave reference frames, a here versus there. But the universe plays by different rules. Its expansion isn't something hurtling through space. It's space itself being stretched, carrying galaxies along like buoys on a tidal wave. Next time someone asks where the Big Bang happened, you can tell them, it happened everywhere all at once. And the proof is written in the fading glow of the CMB and the relentless retreat of every distant galaxy, a cosmic chorus singing the same refrain from every possible vantage point. Those underwater training videos of astronauts gliding gracefully in giant pools might look like they're rehearsing for zero gravity, but here's the catch: water doesn't actually simulate space's weightlessness. What it does mimic is something far more practical, the sensation of working in a pressurized spacesuit while manipulating bulky equipment. Neutral buoyancy, the state where objects hover in water without sinking or floating, creates a reasonable stand-in for the cumbersome mobility challenges of spacewalks, not the true free fall of orbit. Dive into the physics behind this and the distinction becomes clear. Underwater, astronauts still feel water resistance against their movements, a sluggish drag that doesn't exist in the vacuum of space. Every turn of a wrench or twist of their body meets liquid pushback, which ironically makes it perfect practice for operating in stiff, inflated suits that resist motion similarly. NASA Neutral Buoyancy Lab, a 12-meter-deep pool holding 6 million gallons of water, lets crews rehearse intricate tasks like repairing the International Space Station's exterior, where precision matters more than floating effortlessly. The water's resistance trains them to compensate for the real hurdles they'll face: stiff gloves, limited visibility, and the mental fatigue of executing complex procedures under pressure. For authentic zero-G training, astronauts turn to parabolic flights, those stomach-dropping airplane maneuvers nicknamed the vomit comet. By climbing steeply and then nosing into a controlled free fall, these flights create 20 to 30 seconds of true weightlessness as the plane's descent matches the acceleration of gravity. Inside the cabin, everything and everyone floats exactly as they would in orbit. Unlike underwater training, which focuses on task simulation, parabolic flights teach astronauts how their bodies behave untethered, how to orient themselves without up or down, how fluids drift unpredictably, even how to suppress motion sickness when the inner ear rebels. The European Space Agency and private companies like Blue Origin now use these flights extensively, proving they're irreplaceable for capturing the disorienting thrill of genuine microgravity. Here's where the myth's persistence reveals a deeper truth about public perception. Underwater scenes are photogenic, crisp, slow-motion footage of astronauts maneuvering in a way that looks space-like. Parabolic flights, by contrast, are chaotic, cramped, and often nausea-inducing, with footage that rarely makes for glamorous PR reels. Yet every astronaut will tell you, floating in a plane's brief weightlessness comes closer to space's reality than any pool ever could. The next time you see an astronaut training underwater, remember they're not learning to float. They're mastering the art of working under constraints, proving that sometimes the best way to prepare for the infinite freedom of space is to embrace the deliberate resistance of Earth's most unforgiving element. And when that plane arcs into its dive and gravity vanishes, that's when they touch, just for a moment, the sublime weightlessness that awaits them beyond the sky. Few cosmic misunderstandings are as stubborn as the idea that the moon's phases, those slender crescents and glowing full disks, are the result of Earth's shadow creeping across its surface. It's an easy assumption to make, especially when you see the moon partially lit and think, Earth must be blocking the sun, but the truth is far more elegant. Moon phases and lunar eclipses are two entirely different phenomena, governed by separate celestial mechanics that reveal just how precisely our moon dances with sunlight. To unravel this, picture the moon orbiting Earth, with the sun's light always illuminating exactly half of it, the side facing the sun. The phases we see depend on where the moon is in its 29.5-day orbit around us. When the moon sits between Earth and the sun, the illuminated half faces away from us, leaving the near side in darkness. That's the new moon. As the moon moves along its path, we begin to see a sliver of that sunlit side, the waxing crescent. By the time it reaches a 90-degree angle from the sun, we see half of the lit portion, the first quarter moon. When the moon is opposite the sun in our sky, with Earth in between, we see its fully lit face, the glorious full moon. At no point in this cycle is Earth's shadow involved. The phases are simply a game of angles, like watching someone walk around a lamp while you stand still. Their face goes from shadowed to fully lit without anything blocking the light directly. Now contrast this with a lunar eclipse where Earth's shadow does play the starring role. These rare events occur only during a full moon, when the sun, Earth, and moon align perfectly in a straight line. Earth casts two shadows, a faint outer penumbra and a dark inner umbra. As the moon glides into the umbra, it doesn't vanish but often turns a deep coppery red, the result of sunlight refracting through Earth's atmosphere, like all the world's sunsets projected onto the lunar surface. Unlike phases, which happen every month, eclipses are fleeting, sometimes years apart, because the moon's orbit is tilted relative to Earth's shadow. Visual learners imagine this: hold a basketball Earth under a bright lamp, the sun, and let a smaller ball, the moon, orbit it. Rotate the moon around you, and you'll see its phases change based on how much of its sunlit side you can see. Now for an eclipse, hold the moon directly behind Earth so the basketball's shadow falls on it. That dramatic blood-red transformation, that's an eclipse. The gentle waxing and waning, pure orbital geometry. The persistence of this myth likely stems from the way language and imagery blur the lines. We say the moon is shadowed during phases, or describe eclipses as the moon disappearing. But in reality, one is a slow cosmic pirouette in sunlight, the other a fleeting alignment where Earth briefly steals the show. Next time you gaze up at a crescent moon, remember, it's not hiding from Earth's shadow. It's just turning its shoulder to the sun, letting us glimpse a fraction of its eternal light, show a reminder that even the simplest celestial events are masterclasses in motion and light. If you've ever pictured the void of space as a uniformly freezing wasteland, you're not alone, but prepare to have that assumption shattered. The reality is far more dramatic. Space isn't cold everywhere. It's a chaotic roller coaster of extremes where temperatures swing from scorching to cryogenic in the blink of an eye. The difference between sunlight and shadow isn't just noticeable, it's the difference between molten metal and liquid nitrogen, all depending on which way an object happens to face. Take Earth's moon as a prime example. Data from NASA, a lunar reconnaissance orbiter, reveals equatorial regions baking at 127 degrees Celsius during the lunar day, hot enough to boil water, while plummeting to minus 173 degrees at night. But here's the kicker: these aren't gradual shifts. Because there's no atmosphere to distribute heat, the transition happens almost instantly along the Terminator line, where sunlight gives way to darkness. A boulder in direct sunlight could be sizzling on one side while its shadowed face remains colder than Pluto's surface. Satellites orbiting Earth face the same wild swings. The Hubble Space Telescope, for instance, must constantly adjust to temperatures ranging from 90 degrees Celsius on its sunlit side to minus 60 degrees in shadow. Engineers combat this by wrapping spacecraft in reflective thermal blankets or using heat pipes to redistribute energy. Without these measures, delicate instruments would warp, crack, or fail outright, like leaving a smartphone alternating between an oven and a freezer. But the real temperature shocker, Mercury, the closest planet to the Sun, despite daytime highs of 430 degrees, areas in permanent shadow like polar craters harbor ice that's remained frozen for billions of years. NASA's Messenger mission confirmed this bizarre duality, a planet where you could simultaneously fry an egg and freeze a glacier, separated by just a few kilometers of terrain. The myth of universal cold likely stems from space's average background temperature, a chilly minus 270 degrees Celsius, just 3 degrees above absolute zero. But averages lie. In the vacuum, an object's temperature depends entirely on its exposure to radiation. ISS astronauts in sunlight report spacesuits overheating within minutes, while those in shadow risk frostbite on uninsulated gear. Even the James Webb Space Telescope's sunshield creates a 500-degree difference between its layers, a necessity to keep instruments cold enough to detect faint infrared light from the early universe. So why does this matter? Because surviving space's thermal extremes is one of engineering's greatest challenges. Mars rovers use nuclear heaters to survive nights colder than Antarctica, while probes like Parker Solar Probe withstand 1400 degrees near the Sun by hiding behind a cutting-edge carbon shield. Every mission must account for these swings, proving space isn't just cold or hot, it's both, often at the same time. Next time you hear someone call space freezing, remind them the cosmos doesn't do moderation. It's a realm of unforgiving contrasts, where mastering temperature isn't about staying warm or cool, it's about surviving the whiplash between them. The idea that advanced extraterrestrials built the pyramids is one of those tantalizing myths that refuses to fade. Promoted by TV shows and books claiming human ingenuity couldn't possibly account for these ancient marvels. But let's unravel this claim thread by thread, because the real story of how the pyramids rose from the Egyptian desert is far more impressive than any alien intervention. Archaeology, engineering, and mountains of evidence point to one undeniable truth: the pyramids are a testament to human skill, patience, and relentless problem-solving. Start with the workforce. Contrary to old stereotypes of slaves toiling under whips, we now know the pyramids were built by skilled laborers, thousands of well-fed, paid workers who left behind traces of their lives near the construction sites. Excavations at Giza have revealed bakeries capable of producing thousands of loaves daily, barracks for rotating crews, and even medical records showing treatments for injuries like broken bones. These weren't oppressed slaves, they were proud craftsmen who signed their work with graffiti like the drunkards of Menkora, boasting of their contributions. The myth of alien builders crumbles when you consider the logistical sophistication required to house, feed, and organize such a workforce for decades. Then there's the engineering. Ancient astronaut theorists often ask, how could primitive people move 2-ton blocks without modern machinery? But primitive is a misnomer. The Egyptians left us a treasure trove of clues. The discovery of a ramp system at Hatnub's alabaster quarry shows how workers used sledges, ropes, and lubricated pathways to drag massive stones. A papyrus from the reign of Khufu, the very pharaoh behind the Great Pyramid, details the transportation of limestone blocks by boat along the Nile. Even the pyramid's near-perfect alignment can be explained by simple astronomy. The Egyptians tracked the stars, using the autumnal equinox to mark true north with astonishing precision. But here's the clincher: the pyramids weren't built in isolation. They're part of an evolutionary architectural chain. Earlier structures like the Step Pyramid of Djoser and the Bent Pyramid showcase trial-and-error experiments with angles and materials that gradually led to the smooth-sided wonders at Giza. If aliens handed the Egyptians blueprints, why would their early attempts look so human? The progression is clear. Each generation learned from the last, refining techniques through observation and sweat. The most damning evidence against the alien hypothesis, though, is Occam's razor, the principle that the simplest explanation is usually correct. Invoking extraterrestrials to explain the pyramids is like using a flamethrower to light a candle. We have hieroglyphs describing construction, tools preserved in museums, and even workers' tombs affirming their pride in the project. Meanwhile, the alien theory offers zero tangible proof. No star maps in the chambers, no futuristic materials, just a refusal to believe ancient cultures could achieve greatness without cosmic help. At its core, the aliens built the pyramids myth is a disservice to history. It strips the Egyptians of their legacy, implying their brilliance needed outside intervention. But when you stand before these monuments, you're not looking at alien handiwork. You're witnessing humanity's ability to dream big, collaborate, and push the boundaries of what's possible using nothing more than ropes, ramps, and relentless determination. The pyramids aren't proof of visitors from the stars. They're a love letter to what people can accomplish when they set their minds to the impossible. And that, in the end, is the most awe-inspiring truth of all. Of all the whimsical myths about space, nothing captures our playful imagination quite like the idea that the moon is made of cheese. This delicious fantasy has popped up everywhere, from medieval fables to Wallace and Gromit's animated escapades. But where did it start? Surprisingly, its roots stretch back centuries, intertwined with folklore that saw the moon's pockmarked surface as a wheel of Swiss or a cratered cheddar. One of the earliest written references appears in a 16th century proverb by English writer John Haywood. The moon is made of a green cheese, likely a metaphor for something absurd, since green cheese at the time meant fresh, unaged curds that would never hold the moon's shape. But the myth took on a life of its own, evolving into a cultural shorthand for gullibility. Tell someone the moon was cheese, and if they believed you, they'd swallow anything. Science, of course, paints a far less edible picture. Lunar samples brought back by the Apollo missions reveal a world of basalt and breccia, volcanic rock and impact-shattered debris, with not a trace of dairy. The moon's crust is primarily composed of minerals like plagioclase feldspar, pyrozene, and olivine, forged in the chaos of its formation over 4 billion years ago. When a Mars-sized object collided with the young Earth, the debris from that cataclysm coalesced into our moon, leaving it with a bone-dry, rocky composition. The cheesy appearance, those cratered plains, are the result of eons of asteroid impacts, their shadows creating the illusion of holes in a cosmic wheel of Gouda. But here's the twist: the moon does share one unexpected trait with cheese. Analysis of lunar soil reveals it carries a faint, lingering scent, described by Apollo astronauts as resembling wet gunpowder or spent fireworks. When crushed under a spacesuit boot, the finely ground regolith releases trapped gases, creating a metallic tang that clings to everything. It's not exactly aged Parmesan, but it's proof that the moon has its own peculiar aroma, one that lingers in the vacuum-sealed samples stored at NASA's Johnson Space Center to this day. The persistence of the cheese myth speaks to something deeper than silliness. It reflects how humanity has always projected familiar ideas onto the cosmos, using what we know to explain the unknown. Before telescopes revealed the moon's true nature, people saw faces, rabbits, and yes, even dairy products in its patterns. But the real magic lies in what we've learned since: that the moon's true story, written in anorthosite and impact glass, is far richer than any fairy tale. Next time you gaze up at its luminous face, remember, it may not be a snack, but it's still a treasure, a time capsule of cosmic history, waiting to be read like the layers of the most extraordinary cheese wheel in the solar system. Light speed isn't just a cosmic speed limit, it's the ultimate time machine, warping the flow of seconds in ways that defy common sense. The myth that time stops at light speed twists a kernel of truth into sci-fi fantasy, but the real science behind Einstein's relativity is even more mind-bending. Time doesn't freeze like a paused video, it slows down relative to other observers in a phenomenon called time dilation. And we're not just talking theory, this effect is so tangible, it's built into the GPS on your phone. Picture this: two identical atomic clocks, one placed on Earth's surface, the other launched into orbit aboard a satellite. According to relativity, the satellite clock, hurtling at 14,000 miles per hour, experiences time slightly faster than its Earth-bound twin, not because time stops up there, but because velocity changes its passage. Meanwhile, Earth's gravity tugs the opposite way, slowing time for the surface clock. The net result: satellite clocks gain about 38 microseconds per day. That might sound negligible, but without daily corrections, GPS locations would drift by miles within minutes. Engineers must account for relativity, or your navigation app would guide you into a lake. Here's where the myth oversimplifies: time doesn't grind to a halt at light speed. It asymptotically approaches zero from an outsider's perspective, but here's the catch you wouldn't notice. If you could ride a photon, impossible for mass-bearing objects, but play along, your subjective experience of time would feel normal. It's the universe around you that would seem to accelerate into a blur, like watching a billion years of cosmic history flash by in an instant. This isn't speculation. Particle accelerators confirm it daily. Muons, subatomic particles with fleeting lifespans, live longer when accelerated to near light speeds because their internal clocks slow relative to lab detectors. The confusion likely stems from the twin paradox, where one twin traveling near light speed returns to find their sibling aged decades more. But even this scenario doesn't involve frozen time, just drastic desynchronization. Time dilation is a two-way street. Each observer sees the other's clock running slow until acceleration or gravity breaks the symmetry. So why does the time stops myth persist? Because relativity is weird. Our brains evolved for a world of steady, universal time, not one where speed and gravity stretch it like taffy. But the next time your GPS guides you flawlessly through rush hour, remember, you're tapping into Einstein's genius, where time bends but never truly breaks. A cosmic dance of seconds that keeps the universe ticking in perfect, if perplexing, harmony. Is the universe infinite? It's a question that feels more like philosophy than physics, something you'd ponder under the stars rather than calculate in a lab. But modern cosmology has turned this cosmic riddle into something measurable, peeling back the layers of our expanding reality to reveal a startling truth. The universe might not stretch forever in the way we imagine. While it certainly extends far beyond what we can observe, the latest models suggest it could have a finite size, one that's simply too vast for our instruments to map its edges. The catch, even if it's not infinite, you could travel forever and never find a boundary. Let's unpack this paradox. The prevailing cosmological model, called lambda cold dark matter or lambdactum, describes a universe shaped by dark energy, dark matter, and ordinary matter, all expanding at an accelerating rate. Based on precise measurements of the cosmic microwave background, the afterglow of the Big Bang, scientists have calculated the observable universe's radius at roughly 46 billion light-years. But here's where things get twisty. That observable bubble isn't the entire universe, just the portion we can see, because light has had time to reach us since the dawn of time. The cosmos beyond our cosmic horizon might be vastly larger, possibly even infinite. Or it might loop back on itself like a video game world where sailing east eventually brings you west. The most tantalizing clues come from geometry. Einstein's general relativity allows for three possible shapes of the universe: flat, closed like a sphere, or open like a saddle. Satellite data from Planck and WMAP strongly favor a flat or nearly flat universe, but with a critical caveat. Even a flat universe could be finite if it has a torus shape like a donut. Imagine Pac-Man's maze. Travel far enough in one direction, and you'd return to where you started, not because space curves visibly, but because topology creates invisible connections. Some theorists suggest the universe's total volume might be at least 250 times larger than the observable part, based on subtle patterns in the CMB's temperature fluctuations. But if the universe has boundaries, why can't we detect them? Blame the speed of light and cosmic inflation. The expansion of space stretches wavelengths and pushes distant regions beyond our observational reach. Even a finite universe could appear infinite to any observer inside it, like an ant on a giant balloon, crawling in circles but never finding an edge. Some simulations hint that if the cosmos loops, we might spot ghostly duplicates of galaxy clusters in opposite skies, a cosmic hall of mirrors. So far, no such duplicates have been found, leaving the question open. The real marvel here isn't just the scale, but the precision of our tools. By measuring slight variations in the CMB's temperature, differences as tiny as 1 part in 100,000, scientists can test whether space is curved or flat. Future observatories like the European Space Agency's Euclid telescope will hunt for even fainter imprints of cosmic topology, probing whether the universe's expanse dwarfs our wildest dreams or folds into an elegant, finite shape. So is the universe infinite? The answer might hinge on definitions. In practical terms, it behaves as if it's boundless, a realm so vast that its edges, if they exist, remain eternally out of reach. But whether infinite or merely unimaginably large, one thing is certain: the cosmos still holds mysteries no myth could ever simplify, and that's the most humbling truth of all. We've journeyed through cosmic misconceptions today, shattering everything from Hollywood's explosive space deaths to the stubborn myth of a cheese-filled moon. But here's what's truly mind-blowing: the real universe is far stranger than any fiction. Who would have guessed that black holes don't suck, the sun isn't yellow, or that astronauts can see stars more vividly than we ever could from Earth? These aren't just fun facts, they're reminders of how easily pop culture morphs science into something more dramatic, more digestible, but ultimately less true. Take the moon's so-called dark side. We've heard it in songs and movies for decades, yet it's pure poetic license, just like the idea that space is a soundless void. Those haunting plasma waves around Saturn prove the cosmos hums with hidden frequencies, even if our ears can't hear them. And let's not forget Venus, the solar system's unsung furnace, outscorching Mercury not by proximity, but by the cruel irony of a runaway greenhouse effect. These truths aren't just corrections, they're invitations to see the universe with fresh eyes, to embrace its messy, counterintuitive brilliance. So here's your challenge. Next time you watch a sci-fi epic or hear a space fact that sounds too wild to be real, get curious. Dig deeper, because every myth we debunk today started as someone's best guess before science set the record straight. Maybe you once believed the Apollo landings were faked or that the Great Wall was visible from orbit. Now you've got the tools to rewrite those stories. The floor is yours. Drop a comment below about the space myth that fooled you the longest. Was it the twinkling stars, the flaming comets, or maybe, just maybe, you held out hope for that lunar cheese? Whatever it is, let's keep the conversation going. After all, the universe isn't done surprising us, and neither are we done learning. Here's to the next batch of cosmic truths waiting to be uncovered, and to the wonder that comes when we dare to question what we think we know.